For today's lesson, what I want to do is first walk through a couple of sample problems that involve IR spectroscopy, and hopefully these are much easier after you've gone through the homework of lesson 14A. This is a good example of a typical IR problem where I'm going to give you a spectrum and then give you some limited choices of molecules, and you have to decide which of these molecules is going to apply to this spectrum. IR spectroscopy is all about functional groups. And so what I would focus on first is that both of these molecules right here contain alkenes. Alkenes typically produce two distinct peaks. A peak for the hydrogen, where that hydrogen is connected to the alkene, generally shows up right above 3,000. So this peak right here at 3,100 is because of the alkene. This is a vinylic hydrogen coming off of the alkene. Benzylic hydrogens coming off of alkenes will also produce that same peak. So this peak here at 3,100 tells me that either one of these two compounds would work. So not that helpful, but you need to know to identify that peak. Then you'll notice there's this peak at about 2,900. That tells me that somewhere in my molecule I have sp3 hybridized carbons that are connected to hydrogens. Well, that's an sp3 hybridized carbon connected to a hydrogen. There's a hydrogen there and two hydrogens right there that all fit that criteria that would make that peak. Well, unfortunately, my other molecule also makes those those peaks as well. Those three hydrogens would account for that peak, and those three hydrogens would account for that peak. So as I'm approaching this IR spectrum, I'm starting at the left, working my way to the right, and I'm trying to identify what functional group would produce each of the major peaks that I'm seeing. This right here is not a major peak. It's a very minor peak. So I'm going to ignore that. These right here are also minor peaks right here. They really don't tend to be even half as tall as most of the peaks in the spectrum. This is a peak I should be able to interpret. It's above 1500, which is an area of the IR spectrum that I should be familiar with, and it's fairly large, and something that occurs right above 1600 is usually a carbon-carbon double bond. And that's a distinct looking carbon-carbon double bond. It's short and it's sharp. It's everything that I would want to see in a carbon-carbon double bond. But that's not helpful because both of these molecules have carbon-carbon double bonds. At 1500 is where I see the carbon-carbon bonding that's common with organic chemistry. And now what I'm doing is getting into the region of the spectrum where I have a lot less confidence. Anything below 1500 is really difficult to interpret unless the peaks tend to be incredibly large, which is exactly what's going on right here. Notice that you have a pair of peaks, one that's just below 700 and one that's above 700. And if you remember from the homework explanation that I gave for the last lesson, that suggests that I have a benzene ring that has M substitution. It's either mono or it's meta. And this compound up here is definitely meta. In fact, the name of this compound, the common name is metaxylene with an X, XY-LNEN, LENE. That's what I meant to say. And so you could also call it M or meta methyltoluene or 1,3-dimethylbenzene. Any of those names would be correct, and that's definitely the compound that would make these two peaks right here. This is that four-fingered region between about 1600 and 2000. The benzene ring tends to produce a series of ripples, and sometimes they're there and sometimes they're not, and sometimes they're there when they're not supposed to be there. So I generally don't get too excited about these peaks unless I'm already kind of pretty sure that I know what the compound is, and then if I see them, that gives me like a little bit more confidence. So like if I'm 90% confident that this is the correct compound just based on those two compounds, then now because of this, I'm 92% confident. Like it's just not that big of a deal. But if you see them, sometimes it makes you feel a little better. So then what would this compound spectrum look like? Well, it looked like this. This diene right here is also going to produce a peak at 3,100. That's because of the hydrogens coming off of the carbon that's part of a pi bond. You have these peaks just below 3,000, which is because of all these sp3 carbon-hydrogen bonds. You get a pretty substantial peak at 1,600. That's the carbon-carbon double bonding. At 1,500 just tells me that I have carbons in my compound. And then I have these two very large peaks that are not in the same position as they were in the previous example. So notice how these hover between 700 and 800. and these ones here are between 900 and 1,000. This is a terminal alkene. When you have an alkene out on the end of a compound, the two hydrogens will tend to make like a scissoring motion when they catch a photon, and the photons they catch typically have wave numbers between 900 and 1,000. These are not, like, you don't have to memorize these, but man, when they show up, they sure make identifying your compound a lot easier. As I explained in the homework, you also see what's called an overtone or an echo peak. This is similar to the concept of a hydrogen atom. When you shine a photon on a hydrogen atom, it can excite the electron from the first level, or the ground state, up to the second level, and that produces an absorption. Or a hydrogen atom can excite an electron, a photon can excite it from the first level to the third level. That also produces a photon. In the same way that when a photon strikes these two hydrogens out here on the end, and they start to make that scissoring motion, opening and closing like that, then they can absorb these photons down here at 900 and 1,000 by going to their first excited state, or they can actually absorb a wave number that's approximately twice the value. So 2 times 900 is 1,800, so that one right there, and 2 times 1,000 is about 2,000, that one right there. That's where the electrons, sorry, the two hydrogens start moving to a second energy level. And that shows up from time to time. That's what we call an overtone. And you can think about it like an echo peak. So this is the spectrum for this compound here. If we had to name this one, it's hexadiene, 1,5-hexadiene with a methyl group at the 3 position. So 3-methyl 1,5-hexadiene. Protons are a shorthand way of describing the nucleus of a hydrogen atom. And those hydrogens, or protons, are all over in organic chemistry, because organic chemistry is the study of carbon compounds that contain a lot of hydrogens. Therefore, if we have a technique that allows us to state something meaningful about the hydrogens inside of these organic molecules, then we know a lot about the structure of these compounds. So this type of spectroscopy is called proton NMR spectroscopy, or hydrogen NMR spectroscopy, and it allows us to determine the amount of electron density that surrounds the hydrogens in the different organic molecules we're looking at. The design of this experiment requires us to place a variety of different nuclei. So these little blue spheres right here represent different hydrogen nuclei. In the nucleus of hydrogen is just a single proton. That proton actually has an inherent spin, and the spin of the proton generates a magnetic field. Those magnetic fields are very weak, but if you put them in a very strong external magnetic field, essentially sandwiching it between a very powerful electromagnet, it will force those hydrogen nuclei inside of water or inside of your hydrocarbons to line up so that their magnetic field, denoted by this red arrow, is going the same direction as an external magnetic field, denoted by this green arrow. The letters that your current textbook uses for an external magnetic field is B with a superscript 0 on it. But this is an indication that there is some type of external magnetic field. And when it does that, it causes most of the protons inside of your sample to line up with that external applied magnetic field. Just like a log floating downriver, you would expect under most situations for a strong river current to force all of the debris to go with that river current. And if you happen to see some of the protons that are going against that river's current, it's because they absorb energy. And the wavelength of the energy that they absorb tells us about the environment of that hydrogen. So this is how we use NMR spectroscopy. In order to generate an experiment, you need to have a population of protons. An alkane has lots of protons, so that's pretty easy to do. And you need to apply this externally applied magnetic field, and that creates an energy division. Protons that line up their magnetic field with the external magnetic field are in the ground state, the low energy state, and protons that line up against that external field are in an excited state. The stronger your magnetic field, the greater the difference between the low energy ground state and the high energy excited state. And this actually makes it easier to collect the data. So chemists are constantly striving for the strongest magnets possible because it generates the largest gap between the energy states of the low energy and the high energy. Most of the time when we talk about magnets in science, we measure the magnetic strength in Tesla. So if you were to buy a magnetic toy at the dollar store, that would be a very cheap magnet. It would have a low Tesla field strength. If you're a scientist and you want a high field strength magnet, you typically produce an electromagnet. So you run electricity through a wire in a coil, and that generates a magnetic field. When you have a very strong magnet, the energy gap between the ground state and the excited state is very high. And so it takes a high energy photon to flip the nucleus from this ground state where it's going with that externally applied magnetic field to the excited state where it's going against, or upstream of the current. And the energy of that photon is often calculated not as units of energy, but as units of frequency. And if you remember, energy and frequency are directly proportional. Most of the photons that we use are in the range of 60 to 1000 megahertz in frequency. So how does magnetic strength affect photon frequency? A stronger magnetic field requires a higher frequency photon. I've used an NMR instrument that I think was a 500 megahertz NMR instrument, and the data that I got out of it was fantastic for the purposes of my experiment. But there is kind of a push for scientists to develop higher and higher field strength magnet NMR instruments, and they are pushing the boundaries of this megahertz. I believe they're at least at 2200 megahertz, and they might even be higher. I imagine by this point they are higher. It gets very expensive, though, to maintain an instrument that uses a high magnetic field strength. So in the laboratories that we use for student instruction, I think we have a 90 megahertz NMR, which is on the definitely on the low end, and not really suitable for a lot of detailed experimentation, but it works great for teaching students the techniques of NMR spectroscopy. You can conduct NMR spectroscopy on a variety of different atoms. They have to have a particular magnetic field with their nucleus. And the ones that we're going to focus on primarily in organic chemistry are the protons found in hydrogen, or carbon-13 atoms found in carbon. Deuterium actually doesn't show up in the NMR the NMR experiments that we run. And so it's actually a useful technique is if you want to silence a particular hydrogen in an NMR experiment, you replace it chemically with deuterium, and then the deuterium hydrogen doesn't show up on the same field as the proton does, so you can actually tell the difference between the two. We'll look at that experiment later on. How does an NMR machine work? Well, if we go back and take a look at the diagram that we used for IR and UV-Vis spectroscopy, we had some photon source. It passed into our chemical sample. Some of those photons were absorbed, and the resulting photons made it to the detector, and that's how we generated a spectrum. In NMR spectroscopy, it's the same concept, although the design is quite a bit different. This blue line right here represents a wire that emits radio waves. The radio waves go into your sample, which is held in a test tube in the center of the NMR machine, which is usually, the ones we have are about the size of a dishwasher, and they carry these little teeny tubes that are about the size of a pencil. So it's a very large instrument to house a very small sample. When the radio frequency, which is what you get when you're dealing with this range of 60 to 1000 megahertz, those are radio waves. So you're shining radio waves at your sample. It's going to absorb some of those radio waves, and then you have an output signal detector that tells you about how the chemical sample interacted with those radio waves, and then that goes off and prints out some type of NMR spectrum. You do need to have this externally applied magnet so that you force all your protons to line up. If this magnet isn't there, then the protons really don't have a higher energy high state or low state, so they're not really going to absorb photons in a meaningful fashion. So now let's describe what the atomic interactions are that occur inside of an NMR instrument. In an NMR instrument, you have this externally applied magnetic field. the externally applied magnetic field is going to cause the proton to adopt, is going to line up with that externally applied magnetic field. And you're going to shine a photon of radio waves at this, and you're going to measure how much energy in that photon is going to be required to get this proton to swim against the externally applied current. If this externally applied current, let's say, has 100 units of energy, and this was just an isolated naked proton sitting inside of your instrument, then it would require 100 units of energy in order to get this proton to swim upstream. But it's not going to be an isolated naked proton. The proton is going to be attached to some hydrocarbon, and that attachment is going to be a bond that involves a pair of electrons. The two electrons inside of this bond, by default, in their lowest energy state, are actually lining up against an externally applied magnetic field. Protons, which are positively charged, line up with it. Electrons that are negatively charged line up against it, right? Usually. We'll talk about the exceptions. So these electrons line up against that externally applied magnetic field. That means that this proton feels the sum. It feels both of these fields. So F-E-E-L, it feels the sum of both of these fields right here. This field, let's say, was 100 units of energy, and the electrons, now they're small and they're not going to be nearly as large as this externally applied magnetic field. So let's say that they have 5 units of magnetic field strength, but they push against it. So 100 pushing one way, 5 pushing the other way, means that this hydrogen right here is going to interact with a net of 95 units of magnetic field strength. Now that would be different if I took off one of these 3 R groups, if I took it off and replaced it with a fluorine or a chlorine, for example. A chlorine is an electron withdrawing group, and it would take these 2 electrons and pull it away from the hydrogen. If you put a chlorine right here and pulled those electrons away from the hydrogen, that would result in this offsetting value. Instead of being 5, it would be something like 3. And because these electrons have been pulled away from the hydrogen by this hypothetical chlorine, then the net field that this hydrogen feels would go up. 100 minus now 3, if this chlorine was out here, is going to result in that hydrogen dealing with 97 units of field strength. So based on how much energy the photon needs in order to flip that hydrogen, because the hydrogens have different chemical environments, that's how we get information about the structure of the molecule at that particular hydrogen. So let's consider 2 different molecules, chloroform and tetramethylsilane. Tetramethylsilane is often abbreviated as TMS, and we use it quite a bit. These are both common solvents that we can use in the organic chemistry laboratory. They're both liquids at room temperature. The proton, or the hydrogen nucleus in chloroform, is highly de-shielded, meaning that the electrons that are supposed to protect it from that externally applied magnetic field have been pulled away by the chlorines. So going back to this example right here, in chloroform, it would be as if I took all 3 of these R groups and replaced them with chlorines. And that would pull all this electron density so far away from this hydrogen that it really wouldn't get any substantial shielding. So instead of 100 being offset by 5, it would be 100 being offset by, let's say, 0.1. And this hydrogen, because all the electron density has been moved off of it by these 3 chlorines, is feeling almost the full brunt of that externally applied magnetic field. And it would require a lot of energy in order to flip that proton against the externally applied magnetic field, because the electrons aren't helping it in any way. The electrons are referred to as shields. The more electrons that you pack around that proton, the easier it is to flip and the lower energy photon you are going to require. Tetramethylsilane is kind of the most extreme example of a shielded proton. There are actually 12 different hydrogen atoms on this compound. All 12 of those are chemically identical to each other. So if I talk about one of them, the story that I'm telling you is the same for all 12 of them. They are fighting with a carbon for the control of the electron density in their bond, but that carbon is winning the tug of war with silicon. Silicon is a very electron-rich atom. The carbons essentially take so much electron density from the silicon that they really aren't that interested in pulling electron density off the hydrogen. So this hydrogen, or this proton, gets a lot of electron density. It is heavily shielded. It's about as shielded as a hydrogen could possibly be. Therefore, the proton in TMS is going to require the lowest amount of energy typically required in order to flip the proton against that externally applied magnetic field. It's highly shielded. Well, the problem is that we have hundreds of thousands of different chemists across the world, at least, conducting these experiments using magnets that have different strengths. And if the magnets have different strengths, then the photons that are required, even to flip the hydrogen of tetramethylsilane, is going to differ. So while these hydrogens are highly shielded, they got lots of electron density that are pushing against that externally applied field, but you give them a very strong magnet, then they're still going to have a relatively high amount of energy that it takes to flip them. So what chemists decided to do is just normalize everything and set TMS is the energy of the photon required to flip one of the protons in TMS is set at 0. And everybody else is compared to TMS. And the reason that we did that is it allows us to generate the same numerical values even though our magnets have different field strengths. So the take-home lesson on this one is the units that we use in NMR spectroscopy are kind of nonsensical. We use ppm, which actually is parts per million, and that's similar to concentration, which makes no sense. We should be talking about the megahertz of the frequencies of the photons that are required to flip these protons, but we don't. We talk about ppm, and that, I don't know where that historically came from, but it allows us to kind of use this system where we always set TMS equal to 0, and then everything else is compared to TMS. And what that does is chloroform, which is highly de-shielded, the electrons have been swept away from the proton onto the chlorines, ends up with a high shift value. That's what this is called, of 7.28. And if you change the magnet and it requires a different energy photon, as long as you continue to set TMS equal to 0, you will predictably see a shift value of 7.28 for the hydrogen in chloroform over and over and over again. This generates kind of some odd words, some different vocabulary that chemists use. So downfield is a higher shift value, and that is to the left. It's this side over here where they have decreased electron density and decreased shielding. Upfield is to the right. That's where you see more electron density and increased shielding. So why does de-shielding shift to the left? Well, higher shift values correspond to higher energy photons, which corresponds to less electron density, which is the definition of de-shielding. So it really is kind of a confusing vocabulary that we use, but when you see these, you kind of have to start at the 0 point and work your way to the left, knowing that the further to the left you go, the less and less electron density is going to be found around the different hydrogens that you're looking at. So if you consider this example like methane right here, in methane you have a single carbon atom that is feeding on the electron density of 4 different hydrogens. And because that is shared between all 4 hydrogens, the carbon kind of takes a small nibble off of each hydrogen. And the resulting shift value is actually pretty close to TMS. TMS is, from the hydrogen's perspective, the best life can possibly be. That's the most electron density you're going to have. And methane, it's pretty close. And so this has a very low shift value. These hydrogens have a lot of electron density. They are highly shielded. If now you consider something like isopentane, which is a simple hydrocarbon, And here are the shift values for each of the different hydrogens. Notice that hydrogens that are symmetrically related have the same shift value. These three hydrogens and these three hydrogens look the same from the molecule's perspective. They are attached to a methyl group, and their shift value is pretty low. It's right around 1. Okay? If that's because this carbon right there gets to take a nibble off of 3 different hydrogens, so it doesn't pull as much electron density off of each hydrogen. But if you have a carbon that can only get electron density from a single hydrogen, then it's going to take its full meal of electrons off of that one hydrogen, that pulls the electrons off of that hydrogen, de-shields it, and you end up with a higher shift value. So methine carbons typically have higher shift values than methylene carbons, because in a methine carbon, there's only one hydrogen to feed the carbon. So the carbon eats more of that one hydrogen's electron density. If there are 2 hydrogens, then the carbon can kind of share its meal between the 2 hydrogens. Both hydrogens still get a fair amount of electron density. And if there's 3 hydrogens, that's kind of best case scenario. But notice that these 3 hydrogens right there actually end up with even more electron density. They're more shielded and have a lower shift value than these 3 hydrogens over here. And hopefully you can kind of see why that is. It's because of their neighbor. This carbon is not getting as much electron density from its neighboring hydrogen, and so it's actually going to start to steal a little bit from the neighboring carbons. And that causes, because this carbon is more de-shielded than this carbon, its neighbors kind of share a ripple effect of that. So the closer you are to a point of high de-shielding, the slightly more de-shielded you will be. A methine carbon is more de-shielded than a methylene, and therefore the methyl groups that are attached to the more de-shielded methine carbon are going to feel that more than the one connected to the methylene carbon. Let's look at this example right here, ethyl chloride. If we were to put this inside of an NMR instrument, what would we see? And the first thing we want to think about is how many different peaks would this show in my NMR spectra? Or how many different types of hydrogens are there? And you might say, well, there's 5 hydrogens. I can count, that's easy. And so would we see 5 different peaks in the proton NMR spectrum? And the answer is no, because these 2 hydrogens right here are actually chemically identical to each other. Okay? And they will produce the exact same peak in my proton NMR spectrum. And these 3 hydrogens out here are also chemically identical to each other, and they will produce the same peaks in the proton NMR spectra. What I mean by this is when I conduct an experiment and start shining photons at this compound inside of the magnet of an NMR, these 2 hydrogens will absorb photons of a particular frequency that happens to be exactly the same as each other, and these 3 hydrogens right here will absorb photons of a particular frequency of exactly that same value. So I have 2 different types of hydrogens found in my compound, and therefore I will see 2 peaks or areas in my spectrum where photons have been absorbed and don't make it to the detector. One of the ways that they test this is they actually look at the nomenclature of the compound. So this particular compound is called chloroethane. And one of the ways you can test to see if chlorines are equivalent is it's called the chlorine, if you can see if hydrogens are equivalent, it's referred to as the chlorine replacement test. If I take this hydrogen off and put a chlorine on in its place, the new name of the compound is 1,1-dichloroethane. But if instead I take this hydrogen off and replace it with a chlorine, it's still 1,1-dichloroethane. That is what's called the chlorine replacement test. You take the hydrogen off, replace it with a chlorine, and check the name. If the name comes up exactly the same for both of those hydrogens, then it means that those 2 hydrogens are equivalent to each other. They will behave exactly the same in all experiments, and they will produce the same peak in your proton NMR. If I take one of these hydrogens off instead and put it on there, now it's 1,2-dichloroethane. That was different than 1,1-dichloroethane, and that means that this hydrogen and this hydrogen are not the same. But this hydrogen produces 1,2-dichloroethane. This hydrogen also produces 1,2-dichloroethane, and this hydrogen right here produces 1,2-dichloroethane. That means that all three of these are going to produce a single peak in my proton NMR, and these two hydrogens right here are also going to produce a single peak in my proton NMR. When you place chloroethane in an NMR instrument and run the experiment, this is a lot what your data is going to look like. They actually tend to add a small amount of TMS to the sample as well, and that peak is then scaled to 0. You can actually, in the computer that you run the experiment on, some of the programs I've worked with, you can just grab this lower scale right here with your mouse and slide it until that TMS peak is sitting right at 0. And it looks like somebody missed that one a little bit. If you look very closely, it's not quite sitting at 0. The chloroform is a common solvent that we use, and it also has a characteristic peak at 7.28, which looks like it's a little bit off as well. And sometimes they'll add chloroform and not TMS, and then you just grab it and slide it until the chloroform peak shows right up at 7.28. Those two are often used to calibrate your scale. Once the scale is calibrated by whatever you're using as your calibration or your solvent, then the other peaks are coming from your sample. Now, you'll notice that these peaks are split up, and we're going to deal with what that splitting means later on. But for now, just kind of blur your eyes a little bit and pretend that you only have these two peaks, because this is referred to as a single peak, and the individual peaklets are treated individually, and we'll deal with those later. But for now, there are two peaks. A peak that shows up at approximately 1 point, that's about 1.7, and a peak that shows up at about 3.5. These peaks on the right-hand side are the ones that are closest to TMS. They are more shielded, and these hydrogens have more access to electron density. The hydrogens on the left-hand side are closer towards the chloroform. That means that they are more deshielded and have less access to electron density. If we now go back to the structure of the compound and ask ourselves, there were two peaks, so these two hydrogens would have accounted for one of those two peaks. I'm going to put a box around them. And these three hydrogens over here accounted for the other peak. These two hydrogens are definitely closer to the chlorine. The closer you are to the chlorine, the more the chlorine is going to pull electron density away from your hydrogens. So these hydrogens that are closer to the chlorine are going to have less electron density. This is a methylene carbon, the carbon with two hydrogens on it. The methylene carbon is going to be more deshielded. The methyl carbon, the one out here on the end with three hydrogens, is furthest from the chlorine, so it feels the effect of the chlorine less. If the chlorine's effect is weaker, that means that the chlorine does not pull as much electron density off of these hydrogens, and therefore they are more shielded. So when we look at this NMR spectra right here, the ones that are closest to TMS, the ones with the most electron density, will be those methyl hydrogens. The ones that are more deshielded and closer to chloroform are going to be the methylene hydrogens, the ones that are closer to the chlorine. So this is often how we think about what an NMR spectrum is telling us. It's telling us about the electronic structure of the compounds that we're focusing on. And this particular compound has two different hydrogen groups. One of the hydrogens is more deshielded. One of the groups of hydrogens is more shielded. And that makes sense for this particular molecule, chloroethane. Chemdraw has a feature that will allow you to predict what the Proton NMR and C13 NMR that we'll get into later look like for any given compound. So you just highlight the compound, you can go to structure, and predict what the Proton NMR structure will look like, and it gives you the numerical values. And so in the example that I showed you, we predicted that the methyl group would have a lower shift value, and the methylene carbon would have a higher shift value, and Chemdraw actually shows that to you in more explicit detail. Here's the actual numerical value for those hydrogens out here in the methyl group, showing you where that peak shows up in the Proton NMR spectrum, and then also where the methylene hydrogens are and its numerical value in the spectrum. And you could make some modifications to the compound and try asking Chemdraw. So let's put a bromine on there. on one end and a chlorine on the other end, and you can predict what the proton NMR will look like. This one's kind of neat because it shows you that the hydrogens that are closest to the bromine are more d-shielded. We expect that. Bromine's a very electronegative atom and pulls electron density off. Chlorine is even more electronegative, and so it pulls even more electron density off. So it gives you kind of the expected shift values. Fluorines are interesting. So instead of a chlorine and a bromine, let's do a bromine and a fluorine right there. That's not a fluorine. That's a fluorine. And we can now predict the shift values for there. And notice how fluorine causes these values to get quite a bit higher, and that's because of the very high electronegativity of the fluorine. Now it's interesting how it's causing those peaks to get a little more complicated in their structure, and that's a detail that we'll get into later on in the semester. So for now, this right here is just a tool you can use in Chemdraw to kind of take a look at what the different proton NMR spectra would look like. Your homework associated with this lecture is lesson 14b, and I've given you a variety of different hydrocarbons and chlorohydrocarbon containing compounds, and you need to determine how many different proton NMR peaks the molecule would produce, and then you want to number those peaks, or at least kind of figure out what order they're going to fall into. You don't have to come up with the exact numerical values, but you should describe them from most shielded to most de-shielded. If you want, you can draw these molecules in Chemdraw and have Chemdraw determine the correct answer for you. And I hope if you've done that, it's only after you've thought your way through the question, because it really doesn't do you any good to let Chemdraw do all the thinking for you. The second question is one that is a bit ambitious to ask at this point, but I need you to start thinking about these types of questions. And this is what your next exam will primarily look like. I am going to give you 4 different types of spectroscopy and expect you to come up with the one molecule that matches all 4 of those types of spectroscopy. So the first spectrum that you're going to look at is the mass spec. And there is some information in this mass spec that should be apparent to you. But most importantly, it tells you what the molar mass of the compound is. When you're done looking at the mass spectrum, I would jump down to the IR spectrum and start identifying some of the functional groups that are inside of your molecule. Kind of bounce back and forth between the mass spec and the IR spectrum until you have the molecular formula. You kind of know which atoms are in there and what ratio they're at. Then I would go to the proton NMR. This is your proton NMR, typically is on a scale of 0 to 12. And identify that there are 4 different types of hydrogens inside the molecule. Okay? And that's pretty much all you need from the proton NMR for this particular compound. This is a carbon-13 NMR, and you've not been really introduced to C13 NMR in a meaningful way. Very similar to proton NMR, it tells you that there are 4 different types of carbons. So that's all you really need out of that one. And then try to kind of take that information from the mass spec, the IR, the proton NMR, the C13 NMR, and see if you can propose a compound that is a reasonable approximation of those spectra. I don't know that you have quite enough information to be able to actually come up with the correct answer, but the process is what's important right now. The one comment I will make is we're going to deal with this idea of integration ratio a little later on. But the integration ratio is the idea that each of these particular peaks in a proton NMR spectra also tells you how many hydrogens there are. And from left to right, it means that there is one hydrogen that is making this peak. There's one hydrogen that's making that peak. 2 hydrogens account for this peak, and 3 hydrogens account for that peak right there. We'll discuss the ins and outs of integration later on, but for this particular question, you kind of need that information. And if you can add those numbers together, it does tell you that your compound should have 6 total hydrogens. 7 total hydrogens, not 6. 7. 1 plus 1 plus 2 plus 3 is 7.